Let's look at how to synthesize alcohols. Um, if you have done alkenes already, then you know how to do a lot of these syntheses, okay? But we'll go over it one by one. So first of all, we'll talk about alkyl halides. Okay, so the way I've arranged this is we'll take one functional group at a time. So first we'll make alcohols from alkyl halides, which is actually just a substitution reaction, which you have done before with SN1, SN2 reactions. And so if it was an SN2 reaction, then you would go ahead and take a primary halide, treat it with a strong nucleophile, and then do a substitution reaction. For SN1 kind of a mechanism, you need a tertiary halide, not such a strong nucleophile, and then you can still get an alcohol. All right. So in the case of the tertiary halide, the carbocation mechanism is the prevalent one. Okay. But both of them give alcohols, and both of them are fairly okay synthesis. Okay. This, by the way, this is also called solvolysis because here the solvent is also like the nucleophile. Okay, so but both of these are substitution reactions. Now alkenes, there are going to be a lot of reactions here, okay? And this is something that is also mechanism oriented. The previous one, the mechanism was SN1, SN2, right? So explain that a little bit to you. So from alkenes, I will explain a few things that are critical here, but I'm expecting that you already know a lot of these things, okay? So first of all, alkenes will give you only addition reactions. So there's not substitution, okay? So if we're adding something, so here is the general reaction for it, where you have the alkene and then you have the H3O, and it should actually be H3O plus. Okay, so I'm going to add that. At some point, I'm going to add that. So let me go ahead and put that right now. But anyhow, okay, so you have the H3O plus, and that means it's an acidic medium, and then you end up getting an alcohol. Now, what kind of an alcohol do you get? This alcohol is called the Markovnikov addition. So that's the regioselectivity, okay, which means what? It means that the hydrogen goes to the carbon with more hydrogen, and then the other functional group is going to the carbon with less number of hydrogen. Remember, there are two hydrogens here. There's only one hydrogen here. So that's what's going on, okay? And if you want me to write it for you, I can do that too, but that's what it is, all right? So the hydrogen is going to the carbon with more hydrogen. So that's called Markovnikov addition. Anyway, that's going to be the product if you do hydration of alkenes. Hydration meaning you're adding water, but you're not just adding water, you're actually adding acidic water, which means that you're adding water in an acidic medium. What kind of an acid do you use? So generally the acid you want to use here is going to be H2SO4, okay, or H3PO4. You don't want to use the halo acids, okay, so none of the HCl or HBr, none of that. You want to use sulfuric acid or phosphoric acids for this. So what's the mechanism? And that's shown to you here. The mechanism follows that you have the double bond, which is the base. It's going to attack the proton. So once it takes a proton, the proton goes here. I didn't draw it out because, you know, we don't draw hydrogens. So here's the hydrogen there. The carbocation is created here. And this is really what supports the Markovnikov addition, right? Because you form the carbocation that is more stable. If you create the carbocation here, that will be primary. This one is a secondary carbocation. So then you have the water coming in as the nucleophile attacks over here. Remember, don't let go of this hydrogen until you're ready, which means that the water comes in and then picks up this proton. Now you have your alcohol, okay? So you make sure you draw the oxonium ion also as you're writing the mechanism for this kind of a reaction. So this is the general mechanism. Now the problem with this reaction is that you also get rearrangements, okay? So this is not a problem that you get Markovnikov, it's just that this is the only product you will get, okay? That's it. So if you don't want a Markovnikov alcohol, well, then you have an issue, right? But otherwise, no problem, okay? If it's a secondary alcohol you want, then this is a really good synthesis to do. but this is a problem. Rearrangement is an issue. So here I've given you an example of rearrangements. You should have done this before also at some point. So here you have to kind of see what you're doing, okay? You have to be careful with rearrangements. So the first step is always going to be, of course, that the alkene will attack the hydronium ion. So here this is the acid base attack, and then now you have to kind of look, okay? We didn't do that over here because there was no alkyl group anywhere, but here we have an alkyl group, okay? So once we generate the carbocation, now I have to look around and see, is there anything that I can shift around, okay? Now I can't shift the alkyl group, because if I shift the alkyl group, then I will still have the same kind of carbocation. However, I can shift the hydrogen. So once there's a H shift, which is also called the hydride shift, once you shift the hydrogen, now the carbocation is more stable. So secondary to tertiary carbocation, that's what you form. Why does the shift occur? To form a more stable carbocation. Will a shift occur? Yes, it will. Okay, so if it is possible to have a shift, it will. So which means that the alcohol that you're not getting is the one, you know, with the OH over here. So wherever possible that you're going to have rearrangement, you will have rearrangement. Now the next steps are as usual, where the water is going to attack the carbocation, and then the water will also deprotonate that oxonium ion, okay? So instead of getting the alcohol that, you know, you thought, okay, you know, maybe this is what I'm going to get, which is something like this, you never get that, okay? Because remember, your alkene was here, so you thought maybe you'll get an alcohol here. That never happens, okay? So you have to be careful of rearrangement always. You know, when you form the carbocation, just take a second, look around, see if there is any shift possible. Remember, what you can shift is a hydride, a methyl, a phenyl. That's it. Okay, so if you don't want any kind of a shifting going on or any kind of rearrangement going on, then you do the oxymercuration demercuration, all right? And oxymercuration is using this reagent, which is the mercury diacetate. And this is a two-step process. If you write just this also for me, I'm okay with that. This is just the workup part of it, but then you use the mercury acetate along with, not along with, as a second step is sodium borohydride. And now you get the alcohol. But here I've given you a mixture because what I'm trying to show you here is that there is no rearrangement, okay? So which means this mechanism is not really following the carbocation mechanism. On the other hand, you know, you can also get a mixture depending on the alcohol. So for example, if you were using the previous alcohol that you had and you use this reagent, you know, the mercury acetate, and this is the short form, you know, of writing that, and you will get this, no problem. Okay, so if you wanted to get this alcohol, then you will do oxymercuration, you will not do the acidic hydration. Okay, so that's what we mean that you don't have any rearrangement in oxymercuration. It will still give you the Markovnikov product though, okay? That one you are still going to get, all right? But what if you don't want Markovnikov product? Then you do hydroboration. Hydroboration is done with borane, and borane is a Lewis acid, which is, you know, generally stabilized in tetrahydrofuran, THF. This is not the reagent, this is a solvent also. And what you end up getting in this case is an anti-Markovnikov kind of an addition. So here I've given you an asymmetric alkene where you have this carbon which has no hydrogen and this carbon that has hydrogen. So remember, Markovnikov addition is that hydrogen goes to the carbon with more hydrogen. So hydrogen should have come here, but actually that's not what happens, okay? You get the hydrogen on the less hydrogen carbon, okay? And you get alcohol group on the other carbon. And that has to do with the mechanism, okay? And the mechanism is a little bit of a steric hindrance kind of a thing. And so that's why you end up getting alcohol as the anti-Markovnikov location. So you have three different syntheses for alcohols: acidic hydration, oxymercuration, hydroboration. All of them have their pluses and minuses, okay? So you need to know all these syntheses. The other synthesis of an alcohol from an alkene is halohydrin. The only thing about halohydrin is that not only are you getting the alcohol, you also get a halogen. So here you can either use chlorine or you can use bromine, just those two. You don't want to use iodine or fluorine here. So here you get two groups on there. Okay, so you still make an alcohol, but you're also getting a chlorine. So if I ask you to make an alcohol, this is definitely not the synthesis you're going to give me. Okay, but still it's making alcohol. So I just want to kind of have it out there that you can synthesize an alcohol, and you can also get another group if you want to. Okay, so it depends what you're trying to do. So in this case, when you're adding a halide, when you're doing halohydrin formation, then you add the chlorine first. You get this kind of a chloronium ion, and then the water attacks from the back side, and then you get the oxonium ion. Then there is the deprotonation of the hydrogen. Now the addition here is what we call anti-addition, because look at them, the stereochemistry, it's on opposite side. That's called anti-addition. You also get the enantiomer. Okay, I'm not writing the enantiomer everywhere, but wherever there is a chiral center, you might also get the enantiomer. Here in this case, a diastereomer too. Okay, and then this also is from alkenes, and you have done this also from in the alkenes chapter, hopefully. And this is where you can take an alkene, treat that with osmium tetroxide and get a diol. So here you're not just getting one alcohol, you're getting two alcohols. Again, what does the synthesis call for? Okay, so when you're looking at a synthesis problem and let's say I give you a problem to make an alcohol. Well, if it is just one alcohol group, this is not the synthesis you're going to use. Okay, however, if there is a call for diol, then yes, you can use this synthesis. Okay, all right, so there are two reagents you can use here. You can either use osmium tetroxide or you can also use potassium permanganate. Both of them are going to give you diols, and both of them will give you what is called a syn diol. Syn meaning that the alcohol groups are coming on the same side. Okay, again, you will have an enantiomer also. I'm not writing the enantiomer. So that's a syn diol. Again, if you don't give me the bottom part, I'm okay with that, okay? Because that's a workup reagent. And then here's KMNO4. Anyway, now if you wanted to make an antidiol, so this is a syn diol, and then if you wanted to make an antidiol, then you have a little bit of a different route, okay? So here you use MCPBA as your first step, and the second step is acidic hydrolysis, okay? So here the MCPBA will actually create an epoxide, and that epoxide can then be opened up using acidic water, and that will give you then the antidiol. So you can see that we have quite a variety of synthesis that you have already done, and also just from alkenes. We have to move forward, okay? We have like 6 syntheses just from alkenes, okay, to make different kinds of alcohols. Okay, so now we get to something new, okay, and this is synthesis of alcohols from carbonyls, okay, and synthesis of alcohols from carbonyls. I need to first kind of go over this little scheme that I have here for you. Okay, so now we are getting into a new part of organic, which is oxidation reduction. You have done a little bit oxidation reduction before. Wherever you add oxygen, it's called oxidation. Wherever you add hydrogen, it's called reduction. So you have done some of this before, but not in terms of carbonyl chemistry. Okay, so I want you to focus here with me. So here is the alcohol. You take the alcohol, you oxidize with a weak oxidizing agent, and you end up getting a carbonyl like this, which is an aldehyde. That aldehyde can also be oxidized to give an acid. Okay, now the back side of it is that you can take an acid and you can convert that to an aldehyde or an alcohol. Okay, so these are the steps that we take in oxidation reduction. The oxidations are all in blue and the reductions are all in red, not for any reason except that those two colors kind of stand out. Okay, so what we are doing right now is synthesis of alcohols. So which means that we are in this red region, okay, over here, because we have to make alcohol. So how can you make an alcohol? You can make an alcohol from an aldehyde, or you can make an alcohol from an acid. If you make it from the acid, look, it's one step away, right, from the aldehyde. So to make an alcohol from an acid, you need a strong reducing agent. To make it from an aldehyde, you can get away with a weak reducing agent because now you're doing only one step, okay? So you have two different kinds of reducing agents, a strong one and a weak one. Now, you're going to be able to interchange these two depending on what you are dealing with, okay? In some cases, you cannot interchange. In some cases, you can. And that's the whole point, okay, is to learn where you can and where you cannot, okay? So we are in this red region right now. Later on, when we are talking about reactions of alcohols, then we will deal with the blue region, which is the oxidizing, okay? Because that's a reaction of alcohols. Okay, so what are the weak reducing agent? What's the strong one? Here it is. That's it. Right now, we're just going to do these two reagents. Okay, so the weak reducing agent is going to be sodium borohydride. The strong one is called lithium aluminum hydride. Lithium aluminum hydride is actually very reactive. You can't even leave it outside on the bench because it will start reacting with the moisture in the air. So water vapor in the air. It's extremely strong. Okay, so and the hydrides here are extremely reactive. So you have to be very careful with these. Sodium borohydride is a little bit more bearable. Okay, and it's a good reagent. The only thing is that it's a weak one, so you cannot use it for the acid. You can use it here for the carbonyl in the middle, which is the aldehyde, or the ketone, as we are going to learn, okay? So these are your two reagents. NaBH4 is written like this. Lithium aluminum hydride can also be written as LaH, okay? And that's something that we are going to do as we go on, okay? So LaH looks like a airport code, but you know what? That's life, okay? All right. So here we are, okay? This is the reductions, okay, that we are talking about now. So there are two kinds of carbonyls that we are going to use, okay, over here. So I'm just going to, you can read all of this later on if you want, but I'm going to talk about this here. So this is an aldehyde, this is a ketone. You take an aldehyde, which is a terminal group, and you reduce that, you get a primary alcohol. You take a ketone and you reduce that and you get a secondary alcohol, okay? Aldehydes are terminal groups, ketones are internal groups. So internal group will give you an internal alcohol, which is a secondary alcohol. Okay, so depending on what kind of an alcohol you want to make, if you want to make a primary alcohol, you use an aldehyde. If you want to make a secondary alcohol, you use a ketone. You cannot make a tertiary alcohol using this kind of a synthesis. Okay, now one thing I want to point out here is the way that I've written the sodium borohydride and the H3O plus. You cannot use both of them at the same time. As I said, the hydride here is the active component. Okay, so sometimes we write reductions just like that. You will see that in the slide before, that we just write hydride as in like it's a square brackets, and square brackets mean active hydrogen. So hydride is the active hydrogen, and these hydride, okay, extremely reactive. Okay, so even in sodium borohydride, I mean, it is still reactive, is not as strong as lithium aluminum hydride. It was fairly reactive. Okay, and so you have to prevent it from reacting it with water. All right, so this is written as 1 and 2 because you do this in a two-step process. You don't add the acid water along with the sodium borohydride. Okay, so just be careful when you're writing these reagents. Don't write it like this, okay, as in a comma. You have to write it as 1 and 2. Okay, all right, so then I've given you the mechanism here, and the mechanism is that the hydride, which is the nucleophile here, is reacting with the carbonyl. The carbonyl here is the delta positive, and oxygen is delta negative because of that polarity. So that carbon there, the delta positive, is the electrophile. So that gets attacked, and so the hydrogen is here. and then you create an oxide, which then, remember, this is step number 1. In step number 2, then you will go ahead and protonate the oxide to give you the alcohol. Okay, so this is the mechanism, whether you have primary alcohol or secondary alcohol, which means like, you know, aldehyde or ketone, it doesn't matter. That's what happens. Now, synthesis of alcohols from ester or acid. Okay, so now we are actually into the stronger hydrides here. Okay, so the stronger reducing agent is the LAH, which is the lithium aluminum hydride. Okay, really strong. So one has to be careful with this. Okay, when you're doing this in the lab, you have to take all sorts of precautions. All right, and I'm not going to claim that I did this, but it is possible to have your filter paper actually light on fire because there was slight moisture in there. Okay, so we have to be careful. Anyhow, so you take carboxylic acid, for example, and then treat it with LAH, and you get a primary alcohol. Now, acids are terminal groups for sure because you see them out there, okay, hanging out there. Esters are actually internal groups. These are not considered to be terminal groups, but for the purpose of reduction, they will still give you a primary alcohol. Okay, so esters for the purpose of reduction is still considered a terminal group. Okay, so in both of these cases, you're actually getting a primary alcohol. Now, which one is the better one? Do you react an acid or do you react with, you know, ester to give an alcohol? The preferred starting material is an ester. Okay, so acids actually have an acidic proton right there, right? That's why they're called acids, because they have an acidic proton. So that acidic proton can react with the hydride of the lithium aluminum hydride. Okay, so you can actually end up getting an acid base reactions. So a lot of times it's not a good idea to react a carboxylic acid with LAH. So a lot of times what you do is you convert it into another compound. Okay, and we'll do that a little bit later. Right now you can do this, but later we're going to learn a different way of doing this. Okay, and then esters definitely are very easy then, okay, to reduce. So esters are very common to reduce, again, to give you primary alcohols. You cannot use sodium borohydride. It's a weak reducing agent and it will not reduce any acid, okay, or ester. Here are some examples, okay, for reductions. So you have to be careful when you're doing reductions because there are going to be a lot of groups that you encounter as we go on that can be reduced by sodium borohydride or by lithium aluminum hydride. And you've already done reduction also of alkenes before, alkenes and alkynes, and those can be reduced by hydrogenation. Okay, so there's a lot of reducing agents out there and a lot of functional groups out there. So you have to be very careful in what kind of reagent you choose to use. Now, lithium aluminum hydride is the strongest one. Okay, that's the strongest reagent. So which means that whenever you use LAH, you gotta be careful about the other groups also present in there. Okay, so let me take you through these reactions. So first of all, let's look at the first one. So here we have an alkene and an aldehyde. So if you use sodium borohydride here, you can reduce the alcohol. No problem. Alkene, I'm right there. Okay, because alkene does not get reduced, okay, using sodium borohydride. However, if you use hydrogenation, now you can reduce both groups. Okay, so which means hydrogenation can be a problem if you have an aldehyde group along with an alkene. All right, so you either find something else to reduce an alkene. If you don't want to reduce the aldehyde, you find something else, okay, to reduce the alkene. But otherwise, if you use hydrogenation, you're going to reduce both of these groups, okay, in here. So we have to be careful. Now, one thing I would like to mention over here, because this is possible, is because aldehyde is a terminal group. Okay, and actually even for ketone, it's possible that you can also use LAH here. Okay, lithium aluminum hydride. So even if you use lithium aluminum hydride, you cannot reduce this any further than the alcohol. Okay, so whether you choose to use sodium borohydride or lithium aluminum hydride, both are going to be fine. Okay. Now let's look at the next example that I have here for you. The next example here is the one for ester, and you also have a keto group in there. So if you use sodium borohydride, you can reduce just the ketone, but you're not going to reduce the ester. Okay, but if you use LAH, you're going to reduce both of these functional groups. Okay, so you'll get 2 alcohol groups. So here you have to be really careful. What do you want to do? Okay, here if you use LAH, you reduce both. Okay, so it's not a good idea. If you just want to reduce the ketone, then you just do this. If you want to just reduce the ester and not the ketone, well, in that case, you have to wait a little bit, because we are going to do carbonyl chemistry later on, and we will learn about how to protect your groups. Okay, so we'll talk about that later. Anyhow, so that's what happens if you have different functional groups. All right, one of the most important synthesis of alcohols is actually from carbonyls using Grignard reagents. And Grignard reagents are the most versatile reagents. We are going to learn them now, and you're going to be learning about them again and again and again in all the different functional groups that we do, because these are very critical and important reagents. Okay, so first let me introduce you to organometallic reagents. Organometallics means that you have some organic compound that's reacting with any kind of a metal. Now these were kind of a very interesting kind of an innovation, because nobody thought that you could take an organic compound and treat it with a metal. Okay, but once you do treat it with a metal, now what happens is now you have an alkyl group bonded to a metal. So what happens? The metal is definitely going to be the positive, right? It always gives electrons, which means this is the anion. So cation, anion. Because lithium is such a strong metal, such a good metal, electropositive, that the R group is a really, really strong nucleophile. If it's a strong nucleophile, now it can really react with any kind of an electrophile. Okay, so this is extremely reactive. Then the other kind of reagents are, this is the Grignard reagent, the RMgX. The X is there because Mg is 2 positive. So if it's 2 positive, it needs two negatives to go with it. So the halide and then the R group. Now we're going from group 1 to group 2. Lithium is in group 1 and magnesium is in group 2, the alkaline earth metal. So the Grignard here is the R group connected to the Grignard is not as strong of a nucleophile, but it is still pretty strong of a nucleophile. The main difference between these two is that the Grignard reagents are a little bit more controllable, okay, and they're easier to work with. The lithium reagents are really very, very tough to work with, okay, because the R group is very, very strong nucleophile. And then the last reagents that we will study for us, and not in this chapter, but I just want to introduce them to you, is the dialkyl cuprate reagents. Okay, and so the R2CuLi, these are a little bit different. Now you have copper, which is a transition metal, is not as metallic as even magnesium. So this R group is not as strong of a nucleophile, and copper lithium reagents actually give us very different kinds of products. So these kind of reactions, you can't even, they don't even behave like organometallics like this. They give you very different kind of products. So that's why they're studied. Very unusual kind of reactions. Okay, and so we will study them when we do that. As far as creating alcohols, as far as synthesizing alcohols, you can use either the lithium reagents or Grignard. Right now I want to focus more on Grignard. So first of all, how do you make a Grignard reagent? To make a Grignard reagent, you need to take any kind of an alkyl halide and treat that with magnesium. You can do that easily in the lab also, okay? So take any kind of alkyl halide, whatever you want, primary halide, secondary, tertiary halide, take that and then you treat that with magnesium and you get your Grignard reagent. Now the Grignard reagent is very reactive, as I said, okay? The R group is very nucleophilic, so which means you have to be very careful which means you have to keep it away from water, okay, because it will start reacting with water also. So just like the hydrides we studied before, very strong nucleophiles, here also Grignards are very strong nucleophiles. You have to work in very nice and clean dry conditions in order to have your reactions work, okay. Now regarding the X over here, what is X? Xyl halogen for us in organic chemistry. So X can be any kind of a halide except for fluorine. So you can use chlorine, bromine, iodine, okay, any of those is going to work, no problems. Okay, now that you have generated your Grignard, let's talk just a little bit about the Grignard reagent itself. The R is the minus here, okay, because the Mg is the positive, right? So this is the 2 positive, this is negative, and then this is negative. First of all, this is supposed to be an ionic bond, okay? But we do write this bond, even though that stands for covalent bond, we still write the bond because it helps us focus, okay, a little bit. Generally, if you have the lithium reagents, we don't write the bond because that's wrong, okay? Ionic bonds don't have that kind of a line between two things. So here also the line is actually a little bit of misleading thing. It should not be there, but if it is not there, sometimes we cannot seem to connect. Okay, like what are we working with? Because R group is just an R group. R group can be something like this and R group can be something like this, right? So where is my Grignard? Is it on this carbon? Is it on this carbon? So we need to know that, right? So either you write the negative there that, okay, this is where your Grignard is, or you just draw a bond. Okay, so here we'll just write MgX. Okay, so that way you know that this is where the carbon anion is, not on the other carbons, because that's an important thing. You need to make bonds there, right? So that's kind of an important thing. Next thing that you need to understand is that the R group here is extremely negative, right? That's the carbon anion. So what happens with the carbon anion? I've written these reactions down here to show you what happens with Grignard if you treat them with water and with alcohol. If you treat them in presence of water, like if you have any water while you're making, your Grignard reagent, then this carbon anion will start reacting with the hydrogen here, and it will pick up that proton from the water. I mean, water is amphoteric, right? It can be either acidic or basic. So here, since it's reacting with the base, it's an acid. So it will donate that proton and your Grignard is dead. Okay, your Grignard reagent is dead now. Now you've created an alkane. So if that was your intention to get rid of the reagent, that's fine. But if you had any kind of water in your reaction system, then you actually just killed your Grignard reagent. Okay, so you have to be careful in doing these kind of reactions, that you don't have any water. So which means our solvent that we use for doing Grignard reactions is not going to be water. It also cannot be alcohol, because alcohols behave the same way. Although we are making alcohols, we can't use alcohols as our solvent here also, because again the same thing, acidic proton. So the CH2 here, the anion will pick up the proton, become an alkane, and boom, there goes your Grignard. So one thing I just want to point out also before I move on is how strong this nucleophile is. Okay, so I want you to look at this alkane. So this whole scheme that I have here, if you look at this, this is an alkane, right? And alkane, as we know, are not considered to be acidic at all. The pKa's are extremely high. Okay, above 50 is the pKa for alkane. Okay, which is really means it's not even an acidic, kind of a reagent. Nothing, no acidic proton whatsoever. Which means that the conjugate base of an alkane is going to be a very strong base. So this is the conjugate base. This is the conjugate base. Okay, so it's an extremely strong nucleophile. If you understand these kind of basic things about these reagents, then you can understand the reactivity, okay, of where I'm coming from, that why they will react with water, why they will react with alcohol like this. Okay, so don't be fooled. Okay, if I give you a Grignard reagent and give you a reaction with water, just write it in an acid base, because just find the proton. Okay, that's how it will work. So very strong nucleophiles. Okay, all right, let's go on. So how does the reaction work? The reaction is very straightforward. Okay, so this is the general reaction that you will have. Now you're reacting with carbonyls. Okay, as far as the reaction is concerned. So here is your Grignard. Right now we've just talked about that you have a Grignard reagent, how we made the reagent. That's it. Okay, now this is the reaction. So you take any kind of a carbonyl. All right, this is a ketone sort of a thing because we have R1, R2. So we'll talk a little bit later about the different kinds of carbonyls you can have. But what's happening here? Look at this. We went from an sp2 carbon to an sp3 carbon. Okay, you went from a double bonded oxygen to a single bonded oxygen here, okay, to give the alcohol. So how did this reaction work? This is how the reaction works. So here's the delta positive. This is just like what I did for hydride, okay, for the reduction. I had H minus here, right, for the hydride. Now I just have the Grignard, which means now I have an alkyl group here. That's all. That's the only difference I have here. So you take the alkyl group. Remember, the carbon anion is the carbon that is connected to magnesium. Don't just randomly pick any carbon, okay? The carbon-carbon bond formation here is really critical, okay? So, and you are forming a carbon-carbon bond, which I am going to talk about, all right? But this carbon is going to be attacking this carbon. Why will it attack this one? Because this is delta positive. Why? Because this is a polar bond right here. So this carbon attacks this carbonyl here. Carbon, electrons move towards oxygen. You get the oxide. The oxide then in the second step is going to pick up a proton, become an alcohol. So here we have our beautiful alcohol that we wanted to make. Okay, so very simple mechanism. Okay, but I do need you to know this mechanism. So here are all the different kind of alcohols you can make from Grignard. Okay, so the first one is primary, then secondary and tertiary. Okay, so Grignard is the same in all of these. What is changing is what kind of carbonyl we are using. Okay, so here the carbonyl is what we call formaldehyde. Okay, formaldehyde is just one carbon, and this is an aldehyde group, okay, with the hydrogen instead of having a CH3 here. So it has only one carbon. So a formaldehyde, let me write the formula here for you so you don't get confused. I can write this better, HCHO. Okay, that's kind of what the formula is. So here's the Grignard, and then you have the carbonyl, and then the alcohol. Remember, the alcohol is always going to form on this carbon, okay, on the carbonyl. Wherever you have the carbonyl group, that's where the alcohol is forming. Okay, so keep your eyes focused on the carbonyl. So here is the Grignard, and now we are using any other aldehyde except formaldehyde. Okay, formaldehyde gives you a primary alcohol. Look at this. So this is OH, this is hydrogen, 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 one R group. Okay, so that's a primary alcohol. Here, if you take any other aldehyde except formaldehyde, then you're going to get a secondary alcohol. So now the R group is going to attach here, but see, there's only one hydrogen now. Okay, so that's a secondary alcohol. And then with ketones, you end up getting a tertiary alcohol. So carbon, carbon, and then the third carbon is coming from the Grignard. And so there's no carbon left here. So now this is a tertiary alcohol. So which means what? Now we have Grignard reagents that can give us primary, secondary, and tertiary alcohols. So now we have such a beautiful synthesis, okay, possible for alcohols. Previously, we were either making diols, or we were making only primary, we were making only Markovnikov, but now we have all of these different varieties possible for us, okay? So here are the examples to go with this, okay? So you understand how this is working. Here is a random Grignard, and then here is the formaldehyde. Now, we can write reactions in many different ways. You know that also. I could have written the formaldehyde here and then Grignard here, right, on the top. So it's just different ways of writing stuff, but you still need to write the 1 and 2, okay, for the H3O plus, because the H3O plus is coming in the second step only to protonate. If you have H3O plus in the beginning, well, there goes your Grignard, okay, that's not working. So be careful with that. So anyhow, so if you have a Grignard and then you have formaldehyde, you get a primary alcohol, okay. So only one carbon is adding, that's it. Grignard with an aldehyde which is other than formaldehyde, now you get a secondary. I've tried to color code this for you so you can see what part is coming from the Grignard and what is coming from the aldehyde. Okay, so that way you can, you know, it's kind of nice to know where the fragments are coming from. And then here's the one with the ketone. So ketone here, I took a phenyl magnesium bromide. The phenyl group then attaches right here, okay, to give you a tertiary alcohol. So one thing I want to point out, first of all, I have a little bit, not an error, but it seems like I forgot the H3O plus here, so I'm going to write that. But what I want to mention here, okay, and this is really, I think, a very interesting part about organic chemistry and especially Grignards, is that you end up forming a carbon-carbon bond, okay? So here was the carbon, and then here is the carbon. Look at this, you end up forming a carbon-carbon bond, okay? It's important for us to identify these things because carbon-carbon bonds are really interesting in organic chemistry, because if you're forming a carbon-carbon bond, it means that one carbon has to be positive, the other carbon has to be negative. And to get a carbon to be positive and carbon to be negative, I mean, you have to generate different reagents, right? And that's what we were able to do here with the Grignard, and then of course with the aldehyde or the ketone. So you know, it's kind of a nice thing. The other thing that a carbon-carbon bond does for us, and here's our carbon-carbon bond, is that you are able to take two fragments and then make a larger molecule with it. Okay, so here you were able to add a whole phenyl group, okay, to a molecule. So the carbon-carbon bond formations actually help you to build molecules, okay? So sometimes you can take two large molecules and make even a macromolecule, okay, out of it. So these are very interesting reactions for that reason also, and of course, making alcohols, okay, which really is our key focus right now. Okay, so you can also make alcohols using Grignards and using esters. Okay, so here is an example, and the example here that I want to show you is to specifically show the importance, okay, the fact that you will use 2 moles of Grignard, okay, over here. So here is an ester group. This ester, whatever it is, it doesn't matter. This could be a methyl group or an ethyl group. It doesn't matter what it is. So long it's an ester, it's fine, okay? And then you take 2 moles of Grignard and see what happens, okay? There are two things that are happening over here. Number one, you have 2 R groups. The R groups are coming from the 2 Grignards, okay? The 2 moles. The other thing that's happening is that you're forming a tertiary alcohol, okay? So this is here a tertiary alcohol. So you can make a tertiary alcohol from a ketone also, and you can make a tertiary alcohol from ester also. The only way you make it from ester is when you will have 2 of the same R groups, okay? In ketones, it's possible for you to have all 3 groups different connected to the alcohol, but not in ester though, okay? All right, here's the mechanism for esters. Now, if you don't remember this one, for me right now, it's totally okay, because we're going to do esters later on in our semester with the carboxylic acids and whatnot. So we'll go over it again at that time. But right now, I have shown you how it works. Okay, so here's the Grignard, attacks the carbonyl. You create an oxide. That oxide then gives back to the carbon here. And the OCH3 here, the ester group here, the methoxy group here is the leaving group now. So that leaves and you end up generating a ketone over here. Now ketones we have worked with before, and that ketone now gets attacked with another Grignard. And then this is how the second R group comes in. So the second Grignard comes in here, and then you end up getting an oxide. That oxide now gets protonated to give you the alcohol. You cannot isolate the ketone in the middle. It's not possible, okay, because everything is happening in the same sort of a pot kind of a thing. And I think I mentioned it before, like, you know, this Grignard is quite reactive. So generally when you're doing these reactions, you generate your Grignard reagent and then you use it up. Okay, I'm not going to say it's going to be in situ, but you generally use it up right away. Okay, because you can't keep any Grignard reagent. Okay, it will react with water also, right? So you create the reagent and you use it up ASAP. That's it. Okay, right away you use it. Okay, so this is from ester. So again, ester, you get two of the same groups, two coming from the Grignard, the same Grignard, and you get a tertiary alcohol. All right. Now we need to talk just a little bit about retrosynthesis, okay? Because generally you will get an alcohol and you'll be asked, okay, how do you make this alcohol using Grignard, okay? Now remember, Grignard are not something you can buy from the store, okay? You have to make a Grignard reagent in the lab using an alkyl halide, okay? So, and here I can see a little bit of an error, so 2-butanol there. Let me cross that out. Okay, so you have to start your reaction yourself using the proper alkyl halide and the carbonyl. So which means that when you're looking at an alcohol, really you should be looking at what kind of an alkyl halide and what kind of carbonyl, okay, I'm going to use. Okay, is it an aldehyde? Is it a ketone? What am I going to use? So the best thing to do first is look what kind of an alcohol do you have. Do you have a primary, secondary, or a tertiary alcohol? If it's a primary, you're in luck because it's only formaldehyde, okay, that you can use. If it is secondary, you can use aldehyde. If it is tertiary, tertiary is more like, okay, is it going to be an ester or is it going to be a ketone, okay? So here we have a secondary alcohol. So because we have a secondary alcohol, we're going to use an aldehyde. Now, what I've shown you here in these two boxes, okay, is that how you fragment your carbons. So remember, you're forming a carbon-carbon bond during Grignard synthesis, so which means that you're going to fragment also a carbon-carbon bond. But where do you break the bond? You always break it near the alcohol, okay? Wherever the alcohol is, that's where your carbonyl is going to be, okay? So look at the first fragmentation. So I fragmented between carbons 2 and 3. So then I just wrote the fragments. This is not the real thing, okay? Over here, this is not the real deal. This is the real deal. So here you have the carbonyl, okay? Here you have the alcohol. So it means that's where you're going to get the carbonyl. Now remember, this is the fragment. That fragment does not have any carbon, which means that's where you put the hydrogen. Carbon number 1 is where the carbon is. So that's where the carbon is. Okay, on the other side, you have 2 carbons. So which means carbons number 3 and 4. And then wherever you have the breakage point, that gets the aldehyde. Whatever side has the oxygen gets the carbonyl, whatever does not gets the halide. So now if you fragment from the other side between carbons number 1 and 2, you can see that this carbon is the one that's going to get the carbonyl. Again, aldehyde, right? Because we already established that this is secondary alcohol, so you are going to get an aldehyde. There's no way you're going to get a ketone, okay? So that fragmentation right here gives you a hydrogen here, and then this is where your carbonyl is. And the other one here, which you only had the 1 carbon, that fragmentation gives you CH3Br, okay? So because you only have 1 carbon, okay? Don't write like this. This is not a good idea. It's just not kosher at all, okay? And don't write like this also. I forgot to do the subscript, okay, over here. So CH3Br, that's what your starting material is. So you can have 2 fragmentations. Why did we have 2 fragmentations? Okay, we had 2 fragmentations because our alcohol was asymmetric. Now, if you had something like this, this is also a secondary alcohol, okay? whether you fragment here or you fragment here, you're going to get the same starting materials, and you can try that on your own. Okay, so in this case, you will only have one retrosynthesis. In the case that I have right now for 2-butanol, you end up having two retrosynthesis, okay, because you have two fragmentations possible. So it depends on your starting material, okay, or your, sorry, excuse me, your product is what kind of starting materials you're going to use and how many retrosynthesis you're going to have. So again, just practice, right? Okay, so here is another one where we have a tertiary alcohol now. So here you can clearly see it's a tertiary alcohol. I got so many alkyl groups kind of had dangling out of there. So if I had like 5 more, it would be an octopus, okay, or 7 more. Anyway, so we have 3 alkyl groups out there. Now, here we have a tertiary alcohol. So I already know, okay, I need a ketone, okay, for sure. But now, because I'm being asked for all kinds of synthesis, for that reason, I'm going to have to see, can I use an ester also, okay, over here. So when I look at my fragment, okay, then I'm going to say, oh, okay, I can see that I have these two groups that are exactly the same. If they are exactly the same, that means I can use ester also, okay, for this. So that's why I have two syntheses over here, one from ketone and one going to be from ester. And again, the only reason I have from ester is because two of the groups are the same, because those two groups are going to come from the same Grignard reagent. Okay, so let's go on and see what kind of retro we have. So here are 3 fragmentations. Okay, so from ketone you can fragment here or here. Now you can fragment the 7, 8 also, but again, ethyl group here, ethyl group there also. So it doesn't really matter whether you fragment between 2 and 3 or 3 and 7. Okay, it's the same thing because you'll get the same kind of an alkyl halide, okay, for that. Okay, so here if you fragment on this side, again, remember, you're fragmenting right next to the alcohol group. So between 3 and 4 is your fragmentation. On 3, you're going to get the ketone. On 4, you're going to get the halide. I didn't write the fragmentations like I did before because hopefully you're getting more comfortable. Okay. So 3 gets the ketone and then 4 gets the halide. And this looks weird, so I wrote it again over here. Okay, it's very awkward looking there. Anyhow, now if you fragment on the other side, so 2 and 3 or 3 and 7, both of them are going to give you the same kind of alkyl halide because your ketone is on 3. So your ketone is on 3 over here. And then on 1 and 2, 2 gets the halide. Okay, and then you can redraw this in a little bit better looking structure. Okay, so that's what the ketone would be like. If you were to use an ester for this one, then for the ester, these two fragments need to come off, the ones that are the same. So fragments, the 1, 2 carbon and 7, 8 carbon, those need to come off, which means that carbon number 3 is where you're going to have the ester. Okay, now I wrote 2 halides here, but really it's the same halide. Okay, so when that will react, you know, ethyl bromide, when you react that with magnesium, you'll get the same thing. Okay, but here this is some things I want to point out is that whatever ester you use here is fine. Okay, you can use an ethyl ester, methyl ester, just, you know, stick to those two, keep it simple. Okay, that's all we need here. So now the other thing I want to mention, I use bromine here. Everywhere I'm using alkyl bromide. You can use chloride also. If you feel like a chlorine that day, you go ahead and use chlorine. Okay, it's fine. Iodide is also okay. Fluorine is not. Okay, so this was another kind of a retrosynthesis for Grignard. All right, so you can use lithium reagents as well and alkanide reagents as well to make alcohol. So here is a lithium reagent, works exactly like Grignard. Okay, so you will, again, if you use a ketone, you're going to get, you know, a tertiary alcohol. All right, and depending on what kind of R groups you have, you can have primary, secondary, or tertiary. Okay, so I think this one I have written it wrong, so this could also be a tertiary alcohol depending on, again, what kind of substance you're starting with. Is it an aldehyde or a ketone? Okay. So then here, in the second one, I have an alkanide ion. Alkanide ion, you've done it in alkynes. So you generate your alkanide ion using an alkyne and then sodium amide, a very strong base. So once you have an alkanide ion, this is also a sort of organometallic, and that organometallic will behave just like any other organometallic, and you treat that with any kind of a carbonyl, you will get an alcohol, and then you also get this functional group. Kind of looks awkward, but you know what? That's what it is. All right, the mechanisms are the same, as it is for Grignard. Nothing fancy, nothing different. Okay, so here are some more synthesis. So retrosynthesis. Okay, so here are some alcohols given, and here are some retrosynthesis given for this kind of an alcohol. So go through it as you wish. Okay, I don't want to go through it because I think I've done enough already. So go through it and let me know if you have any questions, but hopefully it should be all clear. And I think that's all we have for you for the synthesis.